Hello there, fellow cryptographers. Welcome to a briefing and software demonstration. Today's subject is Ethereum stealth payments. My name is Brian. I will explain what these stealth payments are and show you how they work, first in slides and then with a real working example. My work is based on this paper by Vitalik Buterin published last year, An Incomplete Guide to Stealth Addresses. I was just curious to see if it works. Buterin explains the fundamental problem with Ethereum, or one of the fundamental remaining challenges with Ethereum is the lack of privacy. Transacting parties who share personal addresses are exposing their business to each other on a public blockchain. Vitalik presents a simple stealth payment scheme, and later on he presents a more complicated one with separate multiple view and spend keys. I chose to start just by implementing the simple version. Why do we need stealth payments? As an example, we find ourselves in the unprecedented situation in which Alice wants to pay Bob. Let's assume Bob is a merchant and Alice is a customer. Alice buys a left-handed widget. When Alice wants to pay Bob, Bob shares his blockchain address. This is a big problem for Bob. He has revealed an address he may be using for other transactions, perhaps all of today's transactions. If Bob is lazy and reuses addresses, then Alice or anyone who learns of the address can see how much business Bob is doing, his range of prices, what time of day he does the most business, and so on. Now, if Bob is not lazy, at the very least he has to make, save, and back up all of the keys for these addresses that he uses throughout his payments. Alice sends payment, and immediately she has the same problem as Bob. Maybe Bob looks at her addresses transactions on the blockchain and notices that Alice is rich. Maybe Bob will charge her more in the future. Now this example may seem a little bit silly, but commercial espionage and the collection and sale of personal information are serious problems. Stealth payments provide a way of separating people from the data trail we leave behind as we do business. Vitalik Buterin's solution begins with the idea of a stealth meta address. Bob wants to receive stealth payments. So he creates a new random 256-bit number labeled small m and shown in red at right. Bob uses elliptic curve math to get the corresponding public key labeled capital M and shown in green. And this capital M is his stealth meta address. Bob shares this M with the world, publishing it on his website, putting it in his email signature block, whatever. Meanwhile, he holds on to small m and keeps it private, because this small m is also known as his root spending key, and he needs it to retrieve any stealth payments later. It's important to note that this small m private key will never be used to make any blockchain transaction. Now Alice makes a stealth payment. She creates a new random private key, small r, calculates the public key from that, and that's labeled capital R. This is called an ephemeral key because it's used once per transaction, and Alice can discard this private key as it's no longer needed after she's made these calculations. Alice posts this ephemeral key in some well-known registry, such as a smart contract. Bob will have to check this same registry later to detect payment. This registry is public and not related to Bob's business in any way. Using some elliptic curve math tricks, Alice generates what's called an asset address labeled capital A and sends payment to this instead of sending it to Bob directly. So Alice actually had to make two transactions. One to post the ephemeral key, and the second one to actually send payment. She doesn't have to post these from the same account, nor does she have to post them at the same time. Please note that this newly computed address A is unique and has never been used on blockchain before. Nobody can tell this payment is related to Bob's stealth meta address. There's also no on-chain way to know which key in the ephemeral key registry was used for which payment. Only Alice and Bob will know. As Bob continues doing business, his customers can all use his same stealth meta address to calculate their own ephemeral keys and addresses. Bob and only Bob can calculate the private key for each address, so he owns these funds and can move them along when and as he wishes. Bob would be wise to move the funds along to a mixer or a shapeshifter, or even stealth pay them forward to someone else, all in order to keep his identity away from these transactions. Let's take a closer look at the elliptic curve math. The Diffie-Hellman trick is named after Whitfield Diffie and Martin Hellman, who proved this in 1976. Two strangers anywhere in the world generate random numbers. Someone creates a big random number small m. He takes this scalar and multiplies by a well-known constant called the generator point. This g is a point on an elliptic curve, and the result of multiplying a point by a scalar is another point. Here capital M, and this is the public key. Small m is the private key, and capital M is the public key. Someone else unrelated, some stranger on the opposite side of the world possibly, does exactly the same thing. Creates a random number small r and generates a point capital R, which is another public key. Now our two strangers each take their own private key, their own small m and their own small r, and each multiplies it by the other's public key, and call this S. And this is the trick. Thanks to the miracle of finite sets and modulo arithmetic, our two strangers get the same answer. They can compute a shared secret without having to exchange any secret information beforehand. Now, if our two strangers run their shared secret through the same hashing function, they should also get the same result. Elliptic curve mathematics allows us to do point addition, meaning adding 2 points to get another point on the curve. The result of hashing the shared secret is 256 bits, and this is the right size to be a private key. This private key multiplied by the generator results in a new point that we can add to public key M, and that gives us a new point P. If we run this point P through another hashing function that only keeps the rightmost 20 bytes, then we have an Ethereum address A. And this is the asset address that Alice in our example sends payment to. Bob computes the same hash of the shared secret, and he considers this the private key and adds it to his own private key small m. The result of that is another scalar, a 256-bit private key that we label as small p. And the neat thing about this is small p is the private key for public key capital P, and therefore small p is the private key that's able to spend the funds that have been placed at address A. And this is the fundamental mathematics behind how the stealth address or the stealth payment mechanism works. In our stealth pay example, Bob published his stealth meta address in a way that Alice and his other payers can retrieve it somehow off-chain. Here Alice has what she needs to post the ephemeral public key and send payment. But how does Bob get Alice's public key capital R? He needs this to derive the private key. He needs to control the funds. The solution requires Alice to post the ephemeral key that she derived from Bob's public key and her private key, and to post it in some public place that Bob's able to read it. This is the ephemeral public key registry. It's really just a list of public keys placed into a smart contract. So Alice computes her value R, and she posts it to this smart contract. And let's just say that for this particular payment to Bob, that the R that she derived was R1337. Now whenever Bob wants to find out if he got paid, or if he wants to move funds, he scans the ephemeral key registry for every key. And then he does the elliptic curve math to find the private key or keys that happen to use his stealth meta address. In our example, Bob notices the private key that turns into an address with funds happens to be that R value. One thing left unaddressed by the solution is, let's say that Bob is receiving lots of payments from different parties. How does he know which R corresponded to which payer? And that is a solution that is, you can tunnel data in Ethereum transactions, so you could put some kind of reference, but that has risks to it. So right now I don't have a solution other than Bob just scans the ephemeral key registry whenever he needs to. And that concludes the slideshow part of the presentation. And now let's move along to a demonstration of some actual software that does this. Welcome to my desktop. I followed Vitalik's approach from the paper, and I coded a stealth payment web app. I'll just bring it up. I've got a web server running on localhost. This is a calculator for the keys and addresses needed to make stealth payments. It doesn't post anything to the blockchain, so users would have to find their own way to post keys and send value to, outside of this app. But here it is in Firefox. The app has three major functions. A receiver can generate a root spending key and stealth meta address. A sender can take a stealth meta address and calculate the ephemeral public key and asset address. And a receiver can use this calculator to scan the ephemeral key registry for incoming payments. Let's start with setting up as a stealth payment receiver. This screen is pretty simple. All we have to do is click on this button, and it'll generate a random number and use that as a primary key and generate the public key for that. So let's give it a try. Okay, so here is the private key, which we're going to use as the root spending key M. And here's the corresponding public key, capital M. And you can tell that this is a compressed public key because it starts with either a 02 or a 03. If it was an uncompressed key, it would start with a 04. But just for brevity, and we keep it just for the sake of ease, we keep it down to compressed format, and present the same here as a QR code in case one was going to scan this and put it into a key registry or something. But I'm not going to use this value. I'm going to generate another one offline and share it for the rest of the scenario, since I don't want to reveal any private key that I'm actually using. So hang on a sec. But before we do that, I'm going to put this down and show the same thing operating in Firefox, or in Tor. So I have it running on an Onion. Bookmarks. And it'll take a second to load over Tor network as the various resources load and get bounced around. And even though those are SVGs, they still take a moment. So here's the same thing running in Tor browser, and it works. I just want to point out one thing, and that is Tor browser puts this grid over top of QR codes because the app tries to draw into an HTML canvas, and you have to explicitly allow that. And so then we can reload the app, having allowed that, and works the same. But just because of the pain factor, I'm going to go back to Firefox. And back to Firefox. try to go back, it's going to give me a warning confirming that I've saved the keys. Now I've generated different keys than the ones shown here. I've done that offline already. So I'm just going to say OK. And now I'm going to play the role of Alice and be the sender. So I'm going to click on the send scenario. And I'm going to use the capital M that I generated offline. And then just click on this calculator looking button here, and that's going to generate R, which is just the public key equivalent of a private key that Alice is going to generate. But then she's going to combine, we're going to combine the various math, and we're going to come up with this address that she's going to send to. So I'm just going to click, and I'm going to save this offline somewhere. And I'm going to save this asset address. And we're good to go. Now this key here has to get published in an ephemeral public key registry, so that's what I'm going to show next. Okay, I've just brought up the app that I wrote to do things with Ethereum, and here I'm going to call a smart contract. So I can call any smart contract, I just have to give it a couple of values. First it needs the address of the ephemeral key registry, and then it's going to need the ABI, which is also published, and it's just a JSON representation of all the different functions and arguments that are expected. Paste that here. I'm looking for register, because we're going to register a key, and it recognizes the parameter that it wants, pub key, and it's bytes. Now this is the capital R that Alice generated, or the sender generated, using, and it needs the 0x in the front. So just double check. Yep. And I'm going to be very generous with gas. And we need to sign this transaction. All right. Bring up my wallet. And there we go. Let's go back to, now here's the full signed transaction. Let's send that and see what happens. We got a transaction hash, so that means it's happened. It's been posted to the blockchain. So let's go back to the smart contract itself, and we should see a transaction coming soon. Oh, there, it already happened. So there's the details. We've just registered a public key. We can look at the transaction, and we can see the call details. And we can see there the same bytes that I just posted. And this is also published in an event, which we can look at when we look at the smart contract events. And so here it is in the event log. Something was registered, pub key, and the value is this in hex. And that matches what I have. Good. So this is the maiden test flight of this smart contract. Seen here first. And now going back. We're back in the app. Okay, so we've just done the step here where, acting as Alice, we've posted this key in the ephemeral public key registry. And so the next thing we do is we send to that address. And that's something else I'm going to do offline here. And here we are after a short break. Now offline, Alice has sent 0.003 that's 3 Finney. She sent that to the asset address that she derived using her own private key R and Bob's stealth meta key. Or Bob's stealth meta address, I should say. And so yeah, she sent payment. So in theory, Bob should be able to retrieve this. And that'll be what we'll look at next here. And back to the desktop. Now I'm going to be Bob again, and I'm going to see if I can retrieve the private key for that payment. Alright, so now we're going to scan the Ethereum blockchain for incoming payments. It needs the M that I calculated earlier, and I just happen to have that saved in my buffer and hidden so that it's not revealed here to the world. Now it's going to check this registry, which is hard-coded to this app, and it's going to get all ephemeral keys newer than this date, and by default this date is a month ago. So now when I say scan, I have a CGI bin service that's going to hit my Ethereum node to get the answers, but the calculations are done here in the browser. So the only thing that the web server is doing is get balance and get keys. That's it. And I'm going to click. CGI comes back, and it found this address with this amount of balance, and the private key is here, although it isn't being shown. But I've got white text on a white background, so it can still be copy and pasted. And so the next thing I'm going to do is take this private key, and I'm going to move the funds out of the this address and forward them on to somewhere else just to complete the demonstration. But this took a little longer than expected because my Ethereum full node decided to stop syncing about a week ago, and I was getting 0 results and couldn't understand, and I spent about a day and a half troubleshooting my own code when in reality it was I just needed to upgrade my Ethereum node. But anyway, here it is working. And yeah, so next step is spend using this private key, and then anyone who watches this video and wants to check will be able to see this Ethereum address, and they'll be able to see those 3 Finney have moved. So hang on a second, I'll just do that and put this down. And I'm back to my Ethereum transaction tool, and I've just done this. I figured out the amount that I needed to drain that account to 0 based on the price of gas at the time, and there's a signed transaction posted. So let's go back to Etherscan and see if it's moved on. And there it has. So you can see that this is the address, the asset address that Alice created it. She paid to it, and then Bob has moved it along, and Alice didn't know Bob's address at all. She just derived an address, and Bob independently derived a private key, and the transaction happened. And here you can see the funds have gone out and back to the same wallet that started the whole scenario. This concludes our presentation today. Here are a few thoughts to share. First, Vitalik's solution actually works. We followed the approach and performed a real stealth payment on the real Ethereum blockchain. Second, the sender and receiver identities were protected as long as the senders and receivers are careful how they move funds into and out of the asset address. There are some challenges though. Third, The viewer could see the amount of copying and pasting and saving bytes required. Users would have to be quite familiar with how this all works in order to use the calculator correctly. Mistakes would be all too easy. Next, users don't really see it, but the cryptography is actually kind of difficult. It involves some byte fiddling, and that isn't natural in JavaScript. Then doing JavaScript in the browser is another level of difficulty. And the last thing learned from this project was that relying on an Ethereum node has its downfalls. Our backend was out of sync for a while and nobody knew, and it cost us a little bit of time. But apart from that, I can see this technique being used in wallets and other decentralized applications so that the user wouldn't actually have to go through all these steps. It should all be done by software. So again, thanks for your attention, and hope to meet you again in our next edition of Tales from the Cryptography Department.